talking about squares and square roots. So this is my most conceptual way of explaining it to you. So what is the area of this square? You guys can all see that, right? I can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. Or I can say it's a 3 by 3 square, which is 9. What is the side length of this square? 4. I can write it here, or I can write it here. So believe it or not, squares and square roots, this is what we're talking about. Okay? There's a conceptual representation of it. Right? Okay, let's keep going. So what if how could I use algebra to find the area of this square? I want to find the area of the square. Well, I've got, no, it's not 2 times 3. We have squares and square roots. So to find the algebra, I would say 3 squared equals the area of the square, because the side of the square is squared to come up with the area, right? 3 squared is x. So x is 9. You see how I was coming to this, Bryce? Because this is like a conceptual way of looking at it. They're actually physically squares. If I want to know the area of the square, all I have to do is square the side of the square. 3 squared is 9. I'm going to show you. So how do I find the side of this square? The square root. Exactly. So x is going to be equal to the square root of 16. The square root of 16 is 4 squared, which is just 4. So if you want to find the side length, right, or the side of a square, you just square root it. All right, so additive inverses. So when I have a positive and a negative, it makes 0. That's our additive inverse property. Multiplicative inverse property is an x times a 1 over x, right? That gets us 1. That's our multiplicative inverse. So additive makes zeros. Multiplicative makes 1. Now we're going to go into square root inverses. Check this out. So just like I said, right, we've been dealing with quadratics, right? Here's a quadratic. Let me do that in a different color. Here's your quadratic. And we've learned how to graph quadratics, right? Now we're going to solve and graph square roots. But notice the bottom of this square root, so it's an inverse. So an inverse is actually, if you take a dotted line right here, and let's say this was a paper you could fold, if you were to fold on that dotted line, you would get the red one. Another way of doing it is if you had an x comma y, the inverse of this from geometry is what? Y comma x. Okay, so now we're going to apply this to algebra 2. Yes. It's in transformation, yes, but it's not a rotation. It's an inverse. It's almost like a reflection. It's more of a reflection over the y equals x axis. It's a reflection, not a rotation. So it's a reflection over y equals x. Okay? Now, can anybody tell me why this is dotted right here? Why in the world would this be dotted? I can give you a clue. More than that, this is a square root function. Nobody? That's not why, though, just graphically. Why graphically is there a dotted line there indicating that it's not part of the graph? Anybody? I got candy. Malik? What? I'm talking about this right here, this dotted line. Why is it not included in my square root function graph? Keyword function. Okay. Okay, I'll ask the question again, and I'll give you guys an opportunity. Because a function has to pass the vertical line test, right? You can't have an input and two outputs, right? I can't say that, oh, what is the value of the function at 5? Oh, it's 2 and negative 2. That doesn't work. That's not a function, okay? So it doesn't pass the vertical line test, so we say that we can only count the top part of the square root function. That's why square root functions look like this. They're really parabolas on their sides cut in half. So they have all the same properties that you've been learning with the quadratics. They shift the same way, right? They have the same type of rate of change. They have all the same rules, only they're flipped on their sides, and you can't count the underside of them. Okay? All right. That's the big idea. We'll get there. We're not going to do all of that today. All right. So here's an example of a function, right? I've got 3 apples going in. I square them. They go into this function box, and they get squared. What comes out? 9. I wish they're apples, but they're not. This is a graphic. I didn't choose it. I just grabbed it off the internet. But then if I have 9 lemons and I put them in the inverse function box, then what comes out is the 3 apples again. Here's algebraically. 3, if I square it, I get 9. If I square root it, I get 3 again. So they're complete inverses of each other. Okay? Squares and square roots go together. One of them makes things larger. One of them makes things larger by itself. It squares it, makes it bigger. And one of them simplifies it. But they're inverses of each other. They work hand in hand together. All right, squares and square roots. So this is what I want you to think about. What's the root of the area? Where did the area come from? Where did the area come from if I say that this is 100 square feet? Where did that come from? What's the root of that? That means it must have come from a side fence that had a 10 by 10 foot fence, right? It's the root of it. Do you understand where that word is coming from now? Where did the area come from? Where is its root? Its root is 10. You have to use 10 and square it to get 100. Is that starting to help a little bit? Okay. All right, so students will be able to use square roots to solve equations today. All we're going to do is solve, but use some of our Jay, sit up, please. All the way up. All right, so the first thing I'm going to do, the actual first thing I'm going to do, I'm going to duplicate this slide for a second. With all this out of the way, I want to show you something. Oh, where's my cover up? Right here. Without all this. Here's a parent function. Correct? It starts right here. I should have done it in a different color. Starts right here. And it goes like this. That's your parent function. As soon as you apply something to the x, what happens to that parent function? It shifts to the right one, right? It has the same shape and everything. All it does is shift to the right. What if I shift it, so that would be here. Let's make it 4. That way I can move it over a little bit. 1, 2, 3, 4. Has the same shape and everything. It just shifts over. What about if I have, let's see, x squared, and we can either take it down 4, let's take it down 4. I can see it better. Take it down 4, or if I write that in transformational form, it would be this, which I was really impressed with. Some of you on your test were using that. All right, because we're going to be going to this more and more and more and more. That's why I want you to keep seeing it. So what's happening here, right, is it's shifting down 1, 2, 3, 4. Same shape and everything. So the graph is actually making all these transformations. Yes. Yes. And if it's over here with the y, it's just like it's in parentheses, and you have to take the opposite of it. Make sense? Yes. We've been learning this since the first unit, because we did it with lines too, right? First we did it with lines, then we did it with absolute value functions, then we did it with quadratics, now we're going to do it with square root functions. Guess what we're going to do it with next? Cubic, probably, right? That's where we're going, yes. The vertex, we're going to talk about that right now. So we're talking about general shape. And when I look at this, I say, oh, that's a square root, that's a quadratic function shifted down 4. That's what I say to myself. Because I can see the transformation by just looking at it. It's a sketch, it's not perfect, right? I'm going to use some more tools right now to actually graph it. But when I see this, I say to myself, oh, it's just a square root. A quadratic function shifted down. Yes, sir. Yep. I know that that's my parent function. But don't worry about that. It's just a sketch. Well, no, you do. But when I'm thinking about it visually, visualizing it, I'm just sketching. I want to know the shape of it. We can get into those details in this next slide. I'm going to show you how to find all those other tools that you need to actually graph it. But when you're sketching it in your head, you should just be visualizing something that looks like a quadratic, right? Quadratic function. Because it's positive, it looks like that, and somehow it's going to shift. It's either going to go this way, or this way, or this way, or this way. You see what I'm saying? You don't have to be so precise when you're just thinking about it in your head of what it should look like. That's where I want to get you guys to. Not, oh, I don't know what to do, but, oh, I know what that graph should look like. Chris, I need you to take your hat off, please. All right, so now let's actually do it for real. So I'm going to factor it first. I look at this and I say to myself, I have the difference of 2 squares. So I can factor that, nice and easy. It's x and 2 and 2 and plus and minus. So when I factor that, I know I have zeros at x equals 2 and x equals negative 2. I should have been writing these in a different color. All right, so let's put them in a different color. So I have 2 and I have negative 2. What's my axis of symmetry? 0. Right in the middle. My axis of symmetry is 0. And then what would my vertex be? It should be negative 4, right? Because you know it's a shift down 4. But if I wanted to do that, I would say, okay, my axis of symmetry is 0. So if I take this and put 0 into it, 0 plus 2 and 0 minus 2, I know what x is, so I just substitute it in for x. I get 2 times negative 2, which is negative 4. So my vertex is at 0, 1, 2, 3, 4. Which I already knew what this was going to look like. Now I've just confirmed it, and you see, Bryce, now I have actual points. Another way you could do it, Bryce, is by actually just using a table of values and just plugging in numbers. But to me, that's going blind. I'd rather use tools I already know about it. Okay, so there is me graphing it. Now I'm going to solve by square rooting. So I have x squared minus 4 equals 0. My first step is to get my squares isolated. This is not squares being isolated. This is 2 squares on one side. I need 1 square on one side and 1 square on the other side. So I'm going to add 4 to both sides. As soon as I have squares on both sides, I can now do the inverse of squares, which is square rooting. So I'm going to take the square root of both sides. When I take the square root of both sides, This comes out of the square root, so it's just x, but I have to consider plus or minus the square root of 4, which is 2. The reason for that is this is ambiguous. Check this out. If I had 2 and I squared it, what would I get? 4. If I had negative 2, what would I get? 4. So I really don't know whether that's 2 or negative 2 because it's being squared. It's something I don't know, and it's being squared. So when I take the square root, there are 2 different possibilities graphically here, right? You have a possibility of it being negative 2, or you have a possibility of it being positive 2. Jay, I need you to wake up. All right, so I solved this by square rooting it. So I have, my possibilities are x could be positive 2 or negative 2. Like a visual of the roots, that's what we're finding. Roots are the root of the graph. The root of the graph is anything on the x-axis. That's why we keep concentrating on the x-axis. Those are the roots. That's what's controlling the answer to any question that you have. If you come up with some type of question, some type of application problem, your answer is going to be in either the root or maybe the maximum of the graph, and we'll get there later. All right? Yes, Aaron. Yeah, some of them you're just going to factor. Yeah, so we're going to use all of our factoring techniques. What do we have? We have GCF. We have difference of 2 squares. We have perfect square trinomials, and then we just have regular trinomials that we factor to find roots. So we're going to use all of those tools. We've been doing those for 3 days, right? So we're going to do it again with this worksheet, and then we're going to check our work algebraically with square rooting. I'm going to do another one. Yikes. Okay, instead of this one, let me do this one. I'm going to do this one. So what was our first step? Isolating the squares. So how could I isolate the squares? There's a square here, but I don't have a square on the other side. What am I going to do? Add 19 to both sides. What do I get when I add 19 to both sides? 81. Do I have squares on both sides now? So what should I do? When I square root it, I get x minus 1. This is no longer a square, right? It canceled. I have x minus 1 equals plus or minus 9, right? Now I'm going to add 1 to both sides, and I get x equals 1 plus or minus 9. Now I'm leaving it like this because graphically what this means, guys, is that, let me put, and I'm going to get you your homework because I want you guys to start looking at it. Graphically, what this looks like wait for it, it's coming. There we go. Graphically, what this looks like is I have an axis of symmetry at 1. That. And if I were to subtract 9, I'd end up at negative 8. Or I could go ahead and do the math and say, what's 1 plus 9? 10. And what's 1 minus 9? Negative 8. Graphically, algebraically. How would you find the vertex? What could you plug in to find the vertex? 1. The axis symmetry is 1. So if you plug in 1 here, let's do it. Let's find the symmetry. Minus 1 squared minus 19 equals 62. So we'll say 81. So it would be doesn't make sense. Because it's not in function form. This is actually a function at negative 19 and 62. These are, if you split it up, it's two different functions. It doesn't work that way. Jay, I need you to wake up. Then you can't have your eyes closed. Okay, I'm going to get you your homework. I need to talk to you after class, please. Only two of you here? Graphing, right? Because you've got a quiz tomorrow on a lot. It's going to be. No. None of this that's on here, except for the graphing part, will be on the quiz tomorrow. Everything we've been doing on 1, 2, and 3. I'm going to get your homework stamped really quick. Hopefully by tonight. Yeah, it'll be on School Loop along with the recording, which I need to stop.